what we're basically doing is not just trying to attack data that's encoded in the executable content of a file, but also the data structures content, or I should just say the data content within a file. So a lot of programs and malware and tools, things like that, are going to be working on data that's somehow organized in a manner that's structured for use by the program. So in other words, the way data is structured is supposed to influence a program control flow or program execution flow. We're going to take some time to analyze some data structures. We'll get into the more complicated stuff probably in the next class. I was putting together this lecture and I realized that probably just the numeric encoding and how to analyze that stuff using a debugger probably take up this entire course period. But we'll talk about how data is organized, represented in a manner that's useful for reverse engineering malicious code. Additionally, one thing I will say is also it'll be common to have some on-disk and some in-memory data structures. They aren't executable code, and in many cases you might have a slightly different representation of data when it's living in a file on disk than in memory. And we'll talk about some of that stuff as well, probably in the next class, because it really matters mostly for the more complex data structures. So the first one, some of you are familiar with, some of you may not be, is what they call numeric representation, or Endianness. So this is if your, and this is the core data that most processors are working with, and we probably observed this looking at the disassembly code that I was walking through before, which is all those instructions are primarily working on some sort of numeric data. So we don't really have a whole lot of operations that are designed to work on strings or large arrays, anything like that. We have micro operations that, if used in a certain pattern or used in a certain combination, can be applied to algorithms that are supposed to deal with, say, string data or complex data structures and things like that. But at their core, they're working on doing numeric operations. And likewise, the data they work on is numeric data. So two common methods are used for storing numeric data, both it's called little endian and big endian, where sometimes you might see LSB, or least significant byte, versus MSB, which is most significant byte. And so that's these two right here. These basically have to do with numeric data handling. So what order should the data be stored in? For instance, if you have to deal with a number that doesn't fit in a single byte of data. And so if we go to, say, the English language, the numbers written using the more prevalent, like Arabic numbering system, the number I just grabbed, 1024, is stored in what's called big endian format. And it basically means that when we read it, and even when we say it, we usually start with the largest component of the power series that defines that number. So in this case, I would describe it as 1024. So the first thing I say is this piece right here, 1000. Then I skip over this because I don't have hundreds. But if I did, if it was 1124, I would say 1124. So then I say 20, then I say 4. And that's pretty much, for whatever reason, that's pretty much become our primary convention in describing numbers. However, like for our Intel chips that are like in my laptop and in many of yours, as well as the x86-64 architecture, this also translates to a lot of, maybe not all, but most Android devices and iOS devices and things like that. They typically do the reverse, which is looking at a number, they want to know what the lowest byte is first. So they want to know, in this example, that the first digit is 4 the next digit's 2, the next digit's 0, and the next digit's 1, and work their way up from right to left. So I typically liken this, and I gave a good kind of example right here, is if you take like two really large numbers, so two, say 5-digit numbers, and you're supposed to add them together, normally to do that addition problem, you stack them on top of each other, and then you work from right to left, adding the components of that together and doing the math that way. So even though we read it from left to right, when we're actually doing the calculation, we do the calculation from right to left. And so thinking that way, that's kind of one of the purposes of organizing the data this way for the computer or for the calculator. So the value 27,452, that's a decimal number, and it can be written, if I was to write it as a hexadecimal constant, I would write it this way. So if I was using the hexadecimal numbering system, which is basically base 16 instead of base 10, to put this in a C program or a Java program or a Python program or something like that, I would write it this way. And that is really telling the programming environment that I'm creating a number. The number consists of 2 bytes, and the most significant byte is 6B, and the least significant byte is 3C. So when I'm writing this to tell the programming environment what my number is, I'm still writing it in the form that makes sense to me. So I'm still typing it out with the most significant byte first and the least significant byte last. And then this gets encoded using the sequence of bytes depending upon the Endianness. So big endian again, which is still used by a number of systems. A really common example where you're likely to run into big endian numbers is going to be a lot of network programming when you're dealing with networking hardware and things like that. For some reason, a lot of that had historically used big endian numbers to begin with, and that habit has translated itself along with the IPv4 standard up to now. So in your networking class and similar work applications, you may end up writing code to do this data conversion very frequently, so that when you are sending control command or when you're configuring the network driver or something like that, you end up sending the data in the right order. So, but on our system, or I should say on most of our computers, we're going to be using this format. So talk through this because when you are analyzing memory and trying to read, say, data that a backdoor has stored in memory for some particular purpose, you're most likely going to see the data organized this way. And this is just kind of underscoring the reasoning behind that. So I wouldn't say that either is arguably better than the other. It's all really driven by architecture. So how your computer loads information from memory and also performs its calculations is going to drive which one of these organizations works best for it. Little endian is at least the more prevalent of the two in your modern day computing hardware. So another interesting feature of numeric representation is signedness. So this comes into play when dealing with negative numbers or really large values. So just to save screen real estate, I'm just going to work with 16-bit numbers here. Traditionally, what you'll probably end up working with most of your programs is going to be either 32-bit integers or 64-bit integers. A lot of what we were working with yesterday, or not yesterday, but last week when we were working through a lot of the disassembly examples was primarily 32-bit integers and even some 64-bit ones. So, a 16-bit integer has enough unique configuration space to store 65536 distinct values. So that is 2 to the 16th. So 2 to the 16th power. So that's, there's that many distinct values within, or I should say distinct unique configurations within that many bits. signed 16-bit integer is one that's defined to hold between these two numbers. So, if you exclude the 0, which ends up being the midpoint of those two, then you have an odd number left, which is why the endpoints frequently end up being like this. Or I should say, the endpoints frequently end up looking asymmetric. And that's because if you consider 0 to be a neither positive nor negative number, then you end up with an odd number of values left to be able to choose which ones are going to be negative, and half of them have to be positive. And so they basically put 0 over on the positive side and then get one extra negative number. Unsigned 16-bit integers basically holds the same number of values. It just happens to only hold 0 through as many positive numbers as it can. So in this scenario, the other key feature, and we'll go into a programming example here in a little bit to kind of show how this works. The negative numbers are basically those which have the uppermost bit set to 1. So if you think of it being a string of bits, and bit number 15, or the 2 to the 15 bit, that one can either be set to 1 or 0. And if it's set to 1, then that means that you have all the rest of the bits to basically be able to assign to the different values. So basically partition your set on that one thing, or on that one bit. Rather than merely making the negative numbers be a copy of the positive numbers with that upper bit set, they actually use what's called a 2's complement form. And I actually have a link to that here. So I'm going to copy this up here to kind of give an example of what's going on. So basically, we want to find out how negative 28 would be expressed in 2's complement notation. So first we'd write out 28. So this is what 28 looks like, the positive version of the number. What you end up doing is first you invert all the digits so that 0 becomes 1, 1 becomes 0, and then you add 1 to that value. And then you end up with a number that is how 28 looks like in, or I should say negative 28 looks like encoded in your 2's complement. So you can kind of compare this to this up here and see why, why, or I should say see the difference. So then the question results in why is this the case? And so I gave an example down here where consider that you have 0, so you have a string of all zeros. And we'll actually do this on here, not on this one. Oh. Okay, well, I'll just do this. So, if you have all zeros, so, and then you want to subtract 1 from it, so we'll just do this, subtract 1. Well, first we'll do, if you had 1 and you wanted to subtract 1, right, then that would basically subtract 1 from this and turn that to 0. If you wanted to subtract 1 from it again, if you were to basically say that your negative number was going to be the positive number with the upper bit set, then you'd have to, number 1, add 1 to this, but then have a whole bunch of logic in there to test whether or not you need to set this or not based upon, say, what the whether the old value was 0 or something like that. So you'd basically have to have this logic in place that goes and does a check to determine whether or not it should flip the sign every single time you're doing an operation. They decided a long time ago for efficiency reasons they didn't want to do it, but they did find this useful property, which was that if I have all empty bits and I want to subtract 1 from them, then the natural thing that my processor is going to do, if I just ignore, if I ignore all possible exceptions, is that it's going to actually replace all of them with 1s. So it's going to do what's called a rollover, which is if I'm counting down from, say, 3, that would be 1, 1. And then if I count down 1 more from that, then it would be 1, 0. Then if I count down from that, it would just be 0, 1. Then if I count down from that, it would be 0, 0. Then if I count down from that, 1, 1 would be my next result. So it's called an integer rollover, and they wanted to be able to use that feature to basically do the math and allow you to work with negative numbers without having to create this entire separate negative number handling system in the arithmetic logic unit. So they came up with deciding that negative numbers will be represented using this 2's complement logic. The only consequence of it is that when you're looking in memory at bytes and you don't actually run them through a filter to make them human readable, very frequently the negative numbered bytes don't bear very familiar resemblance to any of the positive number bytes that they would normally correspond to on your normal number line. So, so again, this is a good example of how numeric representation inside the programs can be very, is very processor focused and very processor specific, and therefore it stands to make, stands to reason that you need to, in some cases, have some tool to do math on hand when you're doing analysis or something like that, or at least take this into consideration when you're analyzing data. So I'm going to go over here now and that ends up being pretty readable. So I have a large number of examples here that I'm going to work from today. These right here that I'm selecting are actually the the atomic numbers. So I just kind of gave some random values to all of them, and then I'm going to use a debugger so that we can go and analyze this data. So what I'm going to do is I'm actually going to run it, because I can't remember if I need to or not. So I'm just going to go ahead and run it, but I'm going to set a breakpoint right here. This also ends up being a good example of how to use the GDB tool to go and do analysis. Let me move this further up on the screen because I just realized I'm going to end up standing in front of it. So I'm just going to set a breakpoint there. I'm going to run it just so that it loads everything into memory. Some of the examples I'm going to use later on are actually going to have some code that needs to fill in the data. So let me jump back here and I'll show you. So we're going to look at these 4 values really quick. So first, and I intentionally have these set up so that they have integer values, or I should say decimal values associated with them. So the computer's going to do the decimal to hexadecimal conversion for me, or I should say the decimal to binary conversion, and you'll probably see the hexadecimal version of those when I'm doing analysis. So a really common thing that I end up doing is I'll use the examine command that allows me to examine data that's located in memory. So in this case, I can do examine, and then I can give it a number of bytes. So I can give it, say, 1 byte. I can tell it that I want to see either the hexadecimal representation or even the decimal representation if I want. So I can do db for decimal byte, and then I can give it, you know, so I can give it the address of my variable, and so then this tells me where in memory, so where in program memory at runtime that data is located, and then the data is sitting right here. So there's my 34. If I want to, I can look at it in hexadecimal as well, and in hexadecimal it's 22, which is, this is going to be 2 times 16, so that's 32, plus another 2 is going to be 34. So that's how you get that. So I can use this to go and look at it. If I want, then I can look at the next one, which is SEX. So I made a short, which is going to be a 2-byte example. So I'm going to do this to look at the bytes for that one. And so you'll notice that the address for this one is literally 2 bytes ahead of the address for this one. And then this one ends up having 2b followed by e2. So if I want to go and use Python and do OX 2b e2, right? 2b e2. So 1 1 2 3 4, and if I'm not mistaken, that is this number right here. So I've extracted that number from there. The other thing I can do, because I know these two things are next to each other in memory, is I can go back to this one, and I can actually look at all 3 of them. So I can see, or actually, sorry, all 4 of them. So again, and this is something I didn't point, or I started to point out but I didn't explain, was if you remember, this was a single character. And then when we wanted to display the location, or what is that, SEX, so that the next value down, that ended up being 2 bytes ahead of it. So it wasn't just right next to the character, it was actually 2 bytes ahead of the character. So for whatever reason, the compiler thought that it would make sense that this data gets spaced at an even numbered address. So that's important to take into consideration when you're looking at a program and you're trying to work back to what the author meant. Sometimes you run into situations where the author meant to just put like 3 variables in a function, but when you're analyzing it, it looks like there's actually space for like 4 or 5 different values. And the way that we work back from that is looking through the code that we're analyzing to try and see which memory addresses are actually referenced in any sort of like, mathematical operation or anything, and which ones are never touched. So it's called, say, memory coverage analysis. But as you can see here, if I display, say, all 4 bytes starting at that address, it actually starts to show me that these 2 bytes in this variable are visible in the memory right next to the original one. So it did still collect all the variables that I put together in really close proximity to one another in memory. So the other thing I can do is I'm going to go, and I think this one, yeah, I'll go and look at this one right here, which should be 8 bytes. So in my 64-bit architecture, it's 8 bytes is used for the long values, and then I guess 8 bytes for the long as well. So another thing I can do too, if I want to, is I can I think I can change it. No, I can't. I'm supposed to be, I can edit it after the fact. But what I'm going to actually do is I'm going to jump in here and I'm going to add, say, another integer in here, which is going to be like a 32-bit integer, and then I'm just going to say I'll just do that. Okay, and then so this ends up showing me, so what I ended up doing was I ended up putting a large value right there that ended up being like a number that could be interpreted to be a you know, or a negative number if I was to interpret it as a, say, unsigned integer or as a signed integer. So what I'll do now is I will do this. So I'll say unsigned. I want it to show me what it looks like as an unsigned decimal number. And then I'm going to use so I can actually have the sizes right here. So I've been using byte, but I could use, say, word to show me that value, and that value is right here. So if I was to put this into Python, that's that value. Then, if I wanted to, I could actually put D, and then it shows me what that value is in negative, and you can see those two don't have any correlation to one another. But the important thing is just that, I should say, they don't appear to have any intuitive correlation to one another as far as, like, you know, our human read of them is. One of the things I will say, probably of note, is that the most negative number ends up being, say, the top byte set with all zeros. So so that ends up being that would end up being the most negative, or the lowest negative number in the 4-byte, in the 32-bit number set, would be basically that one. So, and then this one ends up being the number closest to 0. The other interesting thing about that is that then when we're doing less than greater than testing, because again, with negative numbers, the greater the magnitude of the number, the greater the absolute value of the number, the lower the number is from its neighbor, right? Or from its from its neighbor. So the higher magnitude negative numbers end up being less than the lower magnitude numbers, also end up being less than 0. So when they do this two's complement encoding, that also allows it to have this it allows you to compare those two numbers to one another too. It allows you to compare two negative numbers together without always having to do that check. So anyway, so that's kind of how the negative numbers work in a nutshell. And that's, numeric encoding in general. It's important to keep all those rules straight, especially when you're working through the operands that are getting sent, or that I should say are part of the instructions in your disassembly. Because that's the formatting that you're going to see, is that hexadecimal, like byte by byte formatting. I'll go back here just to kind of give it once more.
Why is it displaying different numbers when you give U and B the same?
Oh, okay. Yeah, so the reason it's doing that, and I'll go back up here and show the U, the reason it's doing that is because it is, and then I will also do this, is that these are the 4 bytes that it's supposed to interpret. The same 4 bytes, depending upon whether you have a signed integer or an unsigned integer, are going to represent different values, different human values for that number. So it's almost like, like there's a mapping between it where in one case, so in the unsigned case, your lowest number, or the number that there's nothing beneath, is 0. And then all the numbers are whatever fits in that bit space, whatever fits in that data space, that are greater than 0. In the other case, what they wanted to do was they wanted to get as close as possible to reserving some of the data space for negative numbers and some of it for positive numbers, which means that they had to get rid of about half of the positive numbers and replace them with a mapping to some sort of negative number. So they came up with that funky encoding, the 2's complement encoding, as a way to allow them to reuse the existing mathematical logic that's in the computing components to do all the math, and still provide a way for you to deal with numbers that where some are negative, some are positive. But in order to accomplish that, so remember, both this interval and this interval use the same data representation. So what ends up happening is everything that's greater than that number that would have shown up in this interval actually gets mapped to something that's this number or greater all the way up to 0. So it basically does a mapping between those two. You can almost look at it as a shifting the window on it almost. So in one case, you've got the window set on your number line where 0 is in the dead center, and then you move it slightly this way, and now 0 is on the leading edge of your interval. But you still have the same number of values fit in that on the real, or on the number line. And so that's kind of what they're doing there, is they just move that back and forth. To be totally fair, you can come up with, using the exact same logic, you can come up with all sorts of balances between negatives and positives and stuff like that. And some people do use it that way. In the interest of like compactness and stuff like that, it's it's generally a very efficient approach to try and solve a problem. But these are the 2 most common ones, and these are the 2 that have kind of hard-coded circuitry within most processors to try and handle. So after that, those are kind of the atomic numeric forms. After that, it'll start to become common to find data that's organized in arrays and even matrices, and just kind of use the term matrix as a general purpose term for anything that's greater than one dimension, or greater than one dimensional array. So in this case, a linear array or a one-dimensional array is right here. That's probably the most common non-atomic data structure that many of you are familiar with, and then probably the most common one that you'll run into. And then this ends up being a two-dimensional array, so it's basically got 12, it's a 12 element array, of which each element is actually 3 long values. So it ends up being, and you'll notice I put 4 here. I probably shouldn't have done that because of the, but we'll just assume that this is like a 32-bit machine and 4 is the number of bytes that are in a long integer. Just to kind of give you an idea of the byte representation here. One of the interesting things about this is that also all the elements are guaranteed to be located right next to each other, so located in a contiguous memory space. Additionally, and this is where I'll go to the code example that I had again, and we'll drop down here to the array section. Character arrays have one more way of describing them, and I kind of gave the classic array approach here, which is if I want to make a string of 4 bytes, that's where those bytes are A, B, C, D, I can build it like this. Or if I want, I can make a string that's, say, whatever bytes that is plus 1 by putting a string constant in. But really that just kind of creates a string array. And actually it's not, the way C works is it's not invalid or it's not illegal for me to do that. So if I want to, I can do that. So I'll go and list. And what I'm doing is I'm doing the list function here. Another thing too is when you're dealing with debugging with code where you want to debug it and you want to use the source code and everything, if you're using GCC, use these 2 arguments and it'll make sure that the debugging information is both preserved and also it doesn't do any aggressive optimizations that would cause the code to be unanalyzable. So when you're trying to work through why is my program broken, this is always a really good one to include in there. So back to the program here, I'm going to add another breakpoint here at 43. I'm going to run it. So I'm going to go ahead and look at the memory that's located at each one of these. In fact, I'm just going to go straight to this one and I'll just dump a whole bunch of memory at those locations. So I'll say X and I'll just say 40 ZB, which is that hexadecimal representation, and then and CR test. So then what this ends up doing is it's showing me all the bytes that are located at that. The other nice thing too is that if it does happen to be code that's located also inside of another variable, it's actually showing me that there's some other variables that somehow started in here. Like this one, the second byte is actually here, which means it started over here where the 74 is. But that first thing that I did, which is this ABCD, that's actually right here, so ABCD. So that ends up being the character array right there. Then the string test ended up starting right here, and string test is actually this one. So it's actually my string constant defined, how you're probably very familiar with writing strings in most programming languages. So I'm going to actually show that one now. So you can kind of get it better. One of the helpful features to keep in mind for this as well is that anytime you define a string constant in C, so anytime anyone defines a string constant in C and Pascal and Java and a number of other languages, it is frequently encoded as all these bytes plus space is reserved for a null byte to be on the end of it as well. So whenever, if I was to do this, and this is a big distinction between this way to define a character array and this way to define a character array. Whereas in this one, we'll see like what is this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I think that's 16, I don't know. I'll just do this, because I can't count. So 16. So I can count apparently. So this ends up being 16 bytes plus 1 null equals 17 bytes total. And then this one is exactly 4 bytes. So, and the reason for that is that the way that most systems are used to working, this is just a convention again. This isn't something that's necessarily built directly into the processor or anything. So they could do this in many different ways, and in fact, in the old MS-DOS days, they did do this in different ways. But the most common way of dealing with string data, which is a sequence of characters that you've typed out that's intended to be human readable, the common way to deal with that is display or I should say, perform whatever the string operation is on the data until you run into a character that's not a common human readable character, or in this case, that's the null character. So there's a common terminology that's called null terminated string, and that's what you're going to run into. So when you're dealing with string data, and if you recall, we were pulling a lot of that stuff out of the executable when we're running that strings program on it. That's how that strings program works, is it looks for long sequences of human readable characters. And then it stops pulling out data when it runs into the first character that wouldn't be considered to be human readable. And the reason why it's doing that is because it knows that when I write a program, when I'm authoring something, I'm going to build a lot of character arrays this way that are supposed to have little messages in them, or are supposed to have, little formatting characteristics in them, things like that. So it's trying to separate those out from the other data that might only be machine readable, because the point of that strings program is to give you kind of a summary of the application in a manner that's almost somewhat human readable, so that you can very quickly get a opinion about it. And then finally, there's also, you can define a really long integer array like this. The other nice thing about C is that arrays you don't have to give the number of elements that are in an array when you're defining it like this. So when you're initializing it, it will automatically figure out how many elements are supposed to be in that array and how much memory it should allocate for it, or how much disk space it should allocate for it. So I can go and look at these things again. And I showed you, so this was me looking at the string test. So 74, 68, 69. So these end up being, I can actually do this because it's a lot easier. I'm just going to grab a few of these. So ends up being that sequence, and then I can say basically what I did here was I wrote a for loop that executes this function on every element of A, where every time it runs a loop, it puts it in C. And then after that happened, I generated basically a list of characters. So something very similar to this definition up here. And then Python gives me the ability to join these together with any sort of string. So if I really wanted to, I could also do it like this. So that's just a very shorthand way of rebuilding a string from an array that I use in Python. But the reason I'm doing this is to show you those bytes correspond with this. And so just like we have byte values that describe various numbers in decimal format, or sometimes they describe one negative number, but also in another context, they'll describe a positive number that is a different number. These byte values are also used to describe each one of these letters as well. So each one of these letters has an 8-bit byte value that's unique and associated with it. And as time goes on, you'll actually learn that there are a lot of different encodings where some characters in one encoding are represented by one byte value, and then in another encoding, the same character, the same language character, the same glyph is actually represented by a different number, just because it is, there's nothing core to the processor about it. All it is taking numbers, taking numeric data, and then representing it to us through some sort of filter, like a font or an encoding or something. So then we'll go and look at this data here, which ends up being the array. So I can go and, what do I call that? Yeah, array test. So and I. And this ends up being all the bytes representing this integer array here. I can actually show all of the data words as well. So this is a hexadecimal representation of each of the 32-bit values that are in here. And so you can see here's 1, 2, and then C8 is actually equivalent to 200. So if I wanted to, just like I was changing around U and D and Z in order to get the different encodings presented to me, I can do that here too. So I can show the decimal version of that, which is how we encoded it when we wrote the code and put it in there. And you can see 1, 2, 200, 2000, etc. 42, 42, 40,000, all those things. And likewise, I can go here and I can show what those numeric values are in an unsigned configuration. So like these two are identical. And that's another benefit of this too, of the way that they did the window sliding, is that the values that on the number line are in both sets, their value is actually preserved. It's other numbers that end up getting chopped off to replace new ones that are added on. So like this one, which looks like a really nice value, really nice round value in its negative encoding, is actually a really unintelligible value in its positive encoding. So also when you're looking through data that's being used by the adversary, it's also very important to take into consideration that they might have intended to work with a signed value instead of an unsigned value, or vice versa. And sometimes just trying to show the encoding that way, or even showing it in like the hexadecimal format that I was showing here, showing it in any one of these representations or all of them might be very helpful in kind of giving you some sort of intuition about what they might have been doing with that work. The other thing too that you'll notice is that in this array, every single one of these is actually right next to each other. And likewise, when I was working up here on the character array, it's this one, every single one of those was 1 byte, and they were all right next to each other. And if you remember, when we put the individual character byte up here, so when I had this, and then I had this following it, there was actually a little gap that was inserted by the compiler between those two. If we write the code to be an array like this, it does not appear to insert those gaps. So it's another useful thing to take into consideration when we're going and analyzing data structures after the fact. So the arrays will also always maintain kind of a compact representation, and that allows you to be able to use the subscript to try and interact with each of them. So another thing is is multidimensional arrays. So we'll take a look at those really quick. And this is I 2x2 test, which I don't think is 2x2 anymore, but it was when I first wrote it. So I'm going to show this in the decimal form. Is it decimal? Yeah. But it is short, so I actually want to do this. So the short, or in this case H, so I use the H modifier right here to say that it's what GDB considers to be a half word, which basically means a 16-bit value. So here's 1, 2, 3, 4, 5, 6. So there's 6 total integers there, but they're organized so that there's basically 3 rows, each of which has 2 columns in my array, right? But the way all this stuff was stored in memory is actually these 6 right here. So the program, or I should say the compiler, stored them in memory using the exact same layout that it would have if I would have done this. So both of these actually show up in memory the same way. So the system encodes both of them the same way and organizes them, organizes them in memory the same way. So, and so then another really common matrix layout that you will see is when matrices are sparsely allocated and dynamically allocated at runtime. So an example of that I have here, which is I define a matrix to be 3 rows of an integer pointer, and then each one of those rows, the size of them is undefined. Then I go through to initialize it, and I give it I give it basically each row memory that's going to be 12 integers wide or 12 integers big. One of the very interesting things about this case is that when I do create memory this way, or when I do allocate memory this way and try and create an array this way, I can still operate on it using the same C code that I was using before, but the big difference here is that each one of my rows is not guaranteed to be right next to each other in memory. So when you're dealing with analyzing code that's dealing with dynamic memory allocation, you may be running into situations where each of your rows are located in different sections of memory. So I also allocated, I have this pointer example here, and I did an allocation down here where I stored a bunch of data in it. And so now I can do x again to show you what I'm going to do. So I'm going to do x 3, because I know that there were 3 elements. And then I'm going to say that I want to show this one again, the z hex, and then I want to show or actually I just want to show address. So 3A, because these are going to be memory addresses, because they're pointers, and then I'll just do ptr ex, and I'll have to do that. And so the pointer, so the actual 3 values that are stored in that pointer array are actually 3 different pointers that were allocated at different times. And one thing you can notice is that if you look at the lowest byte here, is that even though we were only allocating like, so I was only allocating 12 bytes, which should be, you know, which should be that value. That's 12. It actually set them offset from each other at about 40, or I should say it placed them 40 bytes offset from each other. So they're not contiguous in memory. But the programmer who's working with this data is going to work with them as if they were, is going to write code that works with them and addresses them as if they were. And that's right here. So that means that I can't necessarily write a program to go and analyze you know, this data by just you know, doing the same thing that I was doing before, like this. I just end up, number 1, looking at pointer data, and number 2, not even looking at the location of memory where my data got stored. So if I want to do that, I end up having to do this. And so these were integer values, so we'll do 12. And so those are, you know, that's the data that I was looking at. Now if I did 24, so 1, 2, 3, 4. If I do 24, I end up with like this random stuff right here. But then I get the next one down here. So there's like, well, there's 16 bytes right here that are set, that are basically separating the 2 rows from each other just because of how the malloc happened to work and the semantics around that. So this is what's called you know, like pointer indirect reference or something, you know, something like that. And you'll run into this case a lot when you're dealing with code that has to for instance, load data from disk, or maybe load data from a packed configuration section or something like that, or maybe even just try and package up data at runtime that I got from the system while it was doing some sort of monitoring on it or some other task. So it's important to kind of keep this example in consideration and think about how this example works, which is that I'm kind of dealing with a pointer, so I have an address to another address. So I'm going to use the address I do have, which I did up here, which is what ptrex was. So it's basically an address. I use that address to find a list of 3 other addresses. And then when I'm doing my analysis, I actually need to jump to each one of those addresses, and I can't rely on the assumption that all the data is going to be sitting right next to each other, so that I can see the data values here. And how do I know that these are my data values? Well, when I wrote it, I made a really simple mathematical function that basically, what is it? It basically sets it to be the value of the index 1 through 12 plus 1, so 1 through 12 instead of 0 through 11, and then that shifts that bit value to the left by whatever row I'm in. So if I'm in row 0, then it shifts it to the left by nothing. If I'm in row 1, then it shifts it to the left by 1, which is also the same as multiplying by 2. And then if I shift it, if I'm in the 3rd row, then I shift it left by 2, which is the same as multiplying by 4. So if I extrapolated this out, so it was 24. So really it should be, you know, so we'll say 24, so 32. That should show us all of them, right? Or almost all of them. Just do 48. And that should give us the whole coverage. Because we know that one of them is at 20, 60, and A0. So here's your 20. So there's your 12 values there. And then here's your 12 values here. And then here's your 12 values here. And so then the last value, which was 12, was multiplied by 4 down here and multiplied by 2 right here. So this is just kind of me using a handful of convenient markers so that I would be able to find this data in memory if I'm looking for it. So, yeah. And so that's, you know, this type of operation being present in code is a very common one that you'll come across as well when you're doing a runtime analysis. So then the final one, I'll kind of leave. I'll leave us ending on this one is C. So, or I should say, struct and class. So in C, struct and class keywords are used to define complex user-defined types. And you might not read this hint in a lot of books or whatever, because a lot of times I don't go into this level of detail, but they really define the same concept in C++. The difference being that for a class, all members are by default private, and for a struct, all members are by default public, from the perspective of a code, I should say API permissions access, that type of thing. So those of you who are familiar with C++, we'll see what that means. But really in a nutshell, that detail is not important other than just to kind of explain what we're going to be looking at and connecting it to the coding concepts that you're probably already familiar with. But frequently these are really just arbitrary collections of atomic data that can also include arrays. So you can put an array inside of a struct. You can put pointers inside of a struct. You can even put other structs or classes inside of a struct, or a pointer to any one of these things. You can put pointer to array, pointer to struct, that type of thing inside of it. So you can build classes, out of classes, out of classes, out of classes, out of classes. Important thing is that atomic data in these is largely stored semi-contiguously. We saw an example of this, say, discontiguous problem earlier when we were looking at that 1 byte value and how it had extra padding inserted. The compiler does the same thing to your struct data as well. And so this kind of gives an example of a struct definition. And what I did here was I just made a data structure to hold an IP address, so a 4-byte IP address, so IPv4, an extra character modifier that maybe is used by a tool somewhere. I don't really give a definition to it other than to say that it's got to be a character, and then a 2-byte port, which is pretty conventional. And then I reflected that up here. So I was running this, and I'm going to go up here and we'll just do 10 ZB, and I will show you the S test data, because that's a struct test data. And so what you can end up seeing is this is basically how you, so I know this is the hexadecimal encoding for 127.0.0.1, or localhost, if you prefer to call it that. I just know that from typing it all the time. So here, if I'm looking at the struct, it ends up getting embedded right here. Then there's this C value. So and that's 63 if you're familiar with the ASCII, or with the hexadecimal value for ASCII C. So that's right here, 63. And then 3000, we can hex 3000, just for the heck of it. It's BB-8. So for all you Star Wars fans, I promise you that was an accident, but a happy accident. So, oops. And so you can see that's right over here. So, excuse me. So BB8's over here. So you have this artifact of a stray 0 being right here again, which is quite odd. But the reason it's there is because the compiler knows, because I've told it that I want to compile this program, this C program, so that it will run on my x86 machine. And so it has built into it a number of rules that say that if the data is packed too close together, then its memory accesses to it are inefficient, and operations run on it are inefficient. So based upon the architecture, it'll actually insert these gaps if the compiler has rules in there that says that, for instance, this is a 16-bit value. It's more efficient for it to start on an even numbered memory location. If it starts in an odd numbered memory location, then it actually, under the hood, the processor ends up having to read memory twice. And that's just how it's built. So you'll run into little artifacts like that that actually differ from CPU to CPU to CPU. So we probably won't work on it too much in this class because it's not my area of expertise, but like mobile stuff is not written in this assembly language that we were looking at last week. It's actually written in ARM64 or just ARM32, which is different assembly language, also has its own different efficiency rules and things like that, and therefore would have data structures lay out slightly differently. So a common way that people avoid having this problem, and I'm actually going to run the, so the program actually tells me what size that value, that struct is right here. A common way that people end up fixing this so it's not, so that it doesn't have any restrictions around it, or it doesn't do that, is they'll actually use this pragma pack around it. So if you set that to 1, then it doesn't insert, it doesn't try and align them to any specific, or I should say it aligns them to any 1 byte offset. So typically it might be set to 2, or it might be set to 4, or it might be set to 8. But if we set it to 1, and then I recompile that program, now the size of that struct is 7, and if I was to main and then break for 3, and then go back up here and grab this again, I can see that now it goes immediately from 63 over to here. So there's ways to override this type of behavior that you may run into as well, and it's worthwhile to keep that in consideration too. This really becomes a big issue for you if you happen to be working with data that, if you happen to be writing a C program to try and work with data, and you're trying to write structs to try and reconstruct what that data is, you'll want to look out for these types of issues when you're trying to map, say, data from a memory dump or from a file on disk or something like that into your own, say, analysis tool memory space. So that said, I believe that's the last slide. So, yep, that's the last one. So that's the end of the lecture for today.
The last line in the code is splitting off the gap in between the pragma pack.
Yeah. So what this ends up doing is it tells it, pragma pack ends up telling it what alignment to use, or what packing alignment to use. So I can go here and I can just search for, yeah. So of course, Stack Overflow, right? Now, Microsoft actually has a much better example, and as well as a number of other ways that it can be used to basically use like temporary alignment, because as you can probably think, you probably do want that behavior on most of your structs, but what you'll do is you'll end up in a situation where there's one example of a struct where you want it to just be, you know, closely packed with no padding in between the elements. So